So let's start off with a review of Euclidean vector spaces. So we start off with the two-dimensional Cartesian plane, which has an x-hat direction and a y-hat direction, or an i-hat direction and a j-hat direction. And vectors are just arrows that point in different locations, and they're described by their coordinates in the plane. So for example, this vector it goes over 2 and up 3, and this vector goes over 3 and down 3. So to add up vectors, geometrically what you do is you move across the first vector, then move across the second vector, and then move from your starting location to your ending location. And algebraically what you do is you add up the components. So for the addition of these two vectors, you add up 2i and 3i to get 5i, and then you add up 3j and negative 3j to get 0j, which means that this moves over 5 and it doesn't move up or down. And addition also satisfies this parallelogram property, which means that a plus b is the same thing as b plus a. That's just saying that vector addition is commutative. And some more technical properties are that every vector a has an opposite vector negative a, so that a plus negative a is equal to 0, which is just 0i plus 0j. And the 0 vector also satisfies that when you add it to any vector, you get that vector itself. So these are some more technical properties, like how you take for granted that addition is commutative and associative without thinking about it too much. So the main concept of vector spaces that are going to be generalized to the Fourier series is the concept of the dot product. So the dot product is what you get when you just multiply each of the components of the vectors and then add them all up together. So for example, with our two vectors 2i plus 3j and 3i minus 3j, the dot product is just 2 times 3 plus 3 times negative 3, which ends up being negative 3. And so often, instead of using a dot between vectors, I'll be using this bracket notation. And the reason for that is later we're going to generalize the dot product to functions. And in that case, it doesn't really make sense to write a dot because you can multiply functions together. And so instead, the bracket notation makes it more clear. So I'll start off using that just so that you get used to it. So the important property of the dot product or inner product is that it satisfies this equality. And that is that the dot or inner product between a and b is equal to the magnitude of a times the magnitude of b times the cosine of the angle between them, as shown in this diagram here. So the way you can derive that is by using the law of cosines, which is a generalization of the Pythagorean theorem. So here you have the third vector c, which is the vector that completes the triangle of a and b. And so by the law of cosines, you have that the magnitude of c squared is equal to the magnitude of a squared plus b squared minus 2ab times the cosine of the angle between them. So if you take this vector c and you move across a and c, you'll realize that you'll just have the vector b. So a plus c is equal to b, which means that c is equal to b minus a. So now the left-hand side of this becomes b minus a magnitude squared, and the right side is magnitude of a squared plus magnitude of b squared minus 2 magnitude of a magnitude of b, cosine of the angle between them. And so the next goal is to be able to expand this left side out. So b minus a, you can component-wise subtract the components, and then you get that the x component of b minus the a component minus the x component of a times I hat plus the y component of b minus the y component of a j hat. And so using the Pythagorean theorem, you can get that the magnitude of a vector squared is just its x component squared plus its y component squared. And this just follows because a vector with its x component and y component forms a right triangle. And so you just have the Pythagorean theorem. And so if you apply that to this vector here, you get that the magnitude squared is equal to bx minus ax squared plus by minus ay squared. And so you can expand this using the binomial theorem, and you get bx squared minus 2axbx plus ax squared for the left one, and by squared minus 2ayby plus ay squared for the right one. So now we can just rearrange terms. So we can take this ax and ay squared, put them up front, then bx and by and put them here, and then axbx and ayby and put them at the end with a negative 2 factored out. And so after simplifying, you can see that by the Pythagorean theorem, this is just a squared again, and this one is just magnitude of b squared. And this expression right here is the same one we have here. So this just becomes the dot product or inner product of a and b. And so moving this down here, you get that the magnitude of b minus a squared is equal to the magnitude of a squared plus b squared minus 2 times the inner product of a and b. And so notice that these two equations are almost identical, except that this one has the inner product of a and b, and this one has a, b, cosine theta, but everything else is the same. So what that means is that these two quantities must be the same, and that's how you get that equality. Okay, so here's a quick proof of a property of the inner product that we'll be using extensively later on. And that is if the inner product of v and w is 0, then v and w are perpendicular vectors. So the way you prove this is we derived earlier that the inner product is the absolute value of v times the absolute value of w times the cosine of the angle between them. And so that means that since by assumption v and w are their lengths are not zero, otherwise you have the zero vector and there's nothing interesting there. Since the product of these three are zero, and neither of these two are zero, the cosine of the angle must be zero. But cosine theta is zero if and only if theta is either 90 degrees or 270 degrees, which implies that v and w are perpendicular. Since if theta is 90 degrees, then you have this angle here, and if it's 270, it's just the other angle all the way around. So the other way is also easy to prove, that if v and w are perpendicular, then the cosine of their angle is zero, and so the inner product is zero. So these two things, that the inner product is zero and that v is perpendicular to w, are two equivalent statements. Okay, so we just got a quick introduction to the inner product, which is defined as the product of the x components of a and b plus the product of the y components of a and b. And so I just rewrote this as a dot b just to show you that there's nothing special about this bracket notation. And we showed that this inner product satisfies the equality that a dot b, or a inner product b, is just the magnitude of a times the magnitude of b times the cosine of the angle between them. And so the reason that this is important is that you can decompose a into two different vectors which are closely related to b. So what you want to do is you have two different vectors a and b, and you decompose a into two perpendicular vectors so that a parallel is in the same direction as b, and a perpendicular is perpendicular to b. So we want to determine a parallel using this dot product. So a vector is determined uniquely by its magnitude and its direction. So the direction of a is the unit vector in the b direction, and that's just the vector divided by its magnitude. So that's going to be something like that. And the reason it's useful to use the unit vector is that you can just write a parallel as a product of its magnitude and its direction. And so its magnitude is also pretty easy to figure out. This is a right triangle, and you have that the parallel component is just one of the legs, and that a is the hypotenuse. So by the definition of cosine, the magnitude of the parallel component is just the magnitude of the vector times cosine theta. Okay. So now you have that a vector is equal to its magnitude times its direction, the unit vector. And so the magnitude is magnitude of a cosine theta. But looking up at this formula, we see that these two are very similar, except without this magnitude of b term. So you can rewrite magnitude of a cosine theta as the inner product of a and b divided by the magnitude of b. Similarly, as we have here, we can rewrite the unit vector in the b direction as b divided by its magnitude. Then you can combine these two together to get the magnitude of b squared at the denominator, then have an a inner product b and the b vector. Now, what's interesting is that the magnitude of b squared is just bx squared plus by squared, whereas the inner product of b with itself is the product of the x components of b, which is bx plus by. Now, bx is just bx squared, and by is just by squared. So the inner product of b with itself just ends up being the magnitude of b squared. Now the parallel component, I'm just rewriting this formula here, is just the inner product of a and b divided by the magnitude of b squared times the b vector. And using this formula up here, we have that this is the same as the inner product of a and b divided by the inner product of b and b times the vector b. And this is going to be very important when we generalize this inner product concept to functions and trigonometric series. Okay, so now I want to give some explicit examples of decomposing a vector. So the vector I'll be decomposing is a, which is 2i hat plus 2j hat. And so the first example is going to be very simple, but it illustrates well the general process. So what we're doing is we're decomposing a vector a into a vector in the x direction and a vector in the y direction. So we have ax times I hat, which is the unit vector in the x direction, plus ay times j hat, which I've written down here. So for ax times I hat, notice that this is just the vector parallel to the I direction, and we're decomposing into a vector in the I direction and a vector perpendicular to the I direction. So by what we saw previously, a vector in a parallel component is going to be the inner product of the vector that you're trying to decompose with the other vector divided by the inner product of the other vector with itself times the other vector. So in this case, you'll have the inner product of a with I divided by the inner product of I with I times the vector I. Now the vector in the j component, we're decomposing it into something parallel to a j component and perpendicular to a j component. So the vector in the j component is similarly going to be the inner product of a with j divided by the inner product of j with a j times j. So the inner product of a with I is just going to be 2 times 1 plus 2 times 0, which is going to be 2. And the inner product of I with I is just going to be 1 times 1 plus 0 times 0, which is going to be 0. And so similarly, the inner product of a with j is 2 times 0 plus 2 times 1, which is 2. And j with j is similarly going to be 1. And so we get that a is equal to 2 over 1 times I hat plus 2 over 1 times j hat, which is exactly what we expected. Now, a more interesting example is using the two vectors 1 plus 2j and -4 plus -4i plus 2j. Now, these two vectors aren't even the same length, but you can easily check that their dot product is 0, and that implies that the angle between them is 90 degrees. So what we want to do is we want to decompose the vector 2i plus 2j into a vector parallel to the v direction and a component perpendicular to the v direction, or in other words, a component in the w direction. So we have a is equal to avv plus aww. So because you're decomposing into something in the parallel direction to v and perpendicular to v, we know that the direction parallel to v is just going to be the inner product of a with v divided by the inner product of v with v times the v vector. And then the second one is just going to be the inner product of a with w divided by the inner product of w with w times the w vector. So the inner product of a with v is just going to be 2 times 1 plus 2 times 2 right here. And the inner product of v with v is just going to be 1 times 1 plus 2 times 2. Similarly, a with w is just going to be 2 times -4 plus 2 times 2. And w with w is just going to be -4 times -4 plus 2 times 2. So the top here is just going to be 2 plus 4, which is 6. Divided by 1 plus 4, which is 5. And this is just going to be -8 plus 4, which is -4. And 16 plus 4, which is 20. So 6/5, you can just leave it as it is. And -4/20 is -1/5. So what this means is that the vector A has a 6/5 contribution of of v, and a -1/5 contribution of w, which makes sense because we're going along the v direction and it's kind of stretched out. And on the other hand, we're going in the opposite direction of w. So we expect it that you have a -w component. So just to double check that this makes sense, we can just plug in the expressions explicitly, and you have 6 over 5 times v, which is I hat plus 2j hat, minus 1/5 w, which is -4 I hat plus 2j hat. So expanding out, you have 6/5 from here and 4/5 from here, and then you have 12/5 from here and -2/5 from here. And so simplifying, you just get that this is going to be 10/5, which is 2i, and this is also going to be 10/5, which is 2j. And as we expected, that's what we get as an answer. Okay, so I just wanted to end off this video with a three-dimensional example of this projection method and then a non-example of a projection method. So you can go through the same steps that we used to derive the formula of projection onto 2 dimensions, and it works in higher dimensions the same way. So for this example, I took 3 vectors u, v, and w, and you can check with the dot product that each of these are mutually orthogonal. And so they're perpendicular to each other, and so we can use the projection trick that we use in 2 dimensions. And so the vector that we're going to be expressing in terms of these 3 is the vector 3i hat plus 5j hat plus 2k hat. Since I'm bad at drawing 3D vectors, I'm just not going to draw this out. But we want to express a as some coefficient a sub u times u vector plus some coefficient times the v vector plus some coefficient times the w vector. So using our projection method, we have that a sub u is the inner product of a and u divided by the inner product of u and u, and similarly for v and w. I should be putting arrows here inside the inner product, but I'm just too lazy. That'll be a lot of arrows. So you can do out the math, inner product of all of these, and then you get that a is equal to 10/3 u plus 4/6 v minus 2 over 2 times w, and that simplifies to a is equal to 10/3 u plus 2/3 v minus w. And so you can check on your own that if you plug in the definitions of u, v, and w here into this, it does indeed give you back your vector a that you started with. So that says that this method of projection works in higher dimensions, and you can use it when you have 3 orthogonal vectors. So for a non-example, consider the 2 vectors u and v, which are I plus j and I plus 2j. Now notice that the inner product or the dot product of u and v is not 0. So that means that u and v are not perpendicular to each other. And so we'll see that the method that we used earlier does not apply here. So the vector that we want to project into some sum of these two is a is equal to 3I hat plus 5j hat. So what we want to do is we want to multiply it as some coefficient times u plus some coefficient as v. And so if you know some linear algebra, you know that that's always possible since these two form a basis of two-dimensional space. However, these coefficients will end up being wrong. And so we're going to call this vector here a prime. So when you do out the calculations, you find that a prime is 8 halves u plus 13/5 v, and that's just the inner products of everything here. And so when you write it all out, you get that's 33 over 5 I hat plus 44 over 5 j hat, if I did my math correctly. And that is most certainly not equal to 3I plus 5j. Weird. So what went wrong? One thing you can look at is taking the inner product of a prime with u. So how you can do that is you take the inner product of this right side with u. And so since the inner product is linear, what that means is that you can just split it up into the inner product of this with the basis vectors. So since this part is a constant, it's just that constant times the inner product of u with u, and then this constant times the inner product of v with u. Now, if v and u were perpendicular, then this would be 0, and this would cancel out the u inner product u, and you would end up with a prime u is the inner product of a and u. But in this case, since these two are not orthogonal, the inner product of v and u ends up being 3, and so you see that the inner product of a prime u and a u ends up being two different values. So obviously then a prime and a cannot be the same vector, because if they were the same vector, then the inner product of a vector with another vector has to be the inner product of the vector with the other vector. So obviously these two can't be the same, and that breaks down because these two are not orthogonal. So that tells us that, you know, we can use this trick if we have orthogonal vectors, and we can use it in like other higher dimensional spaces. And so why did we go through all this work of doing this projection stuff? Well, it turns out that Fourier series is essentially just this projection thing where you consider sine and cosine as being orthogonal vectors of some vector space with some more abstract inner product. And then all you're doing is you're decomposing functions into a sum of these sine and cosine series. So yeah, that's pretty much the idea of how the rest of these videos are going to go for a while. And I'll see you next time where we'll talk about more abstract vector spaces.